All right, now we're going to take a look at inverse functions. So let's look at an example here. Taking into account reaction time, the distance d in feet that a car requires to come to a complete stop while traveling v miles per hour is given by the function d of v is equal to 6.97 v minus 90.39. Accident scene investigators can measure the distance it takes the car to come to a complete stop in the accident and use that information to determine the original speed the vehicle was traveling prior to the accident. To do this, they reverse the formula in what mathematicians call an inverse function. So below is a table of values for the stopping distance of the vehicle. So we have our speeds in miles per hour. We have the distance it took to stop. All right, now this is a problem you've seen before in previous lessons. Solve d of v equals 468.01 for v. So we're looking for the v that we could plug into this function that'll give us a distance of 468.01. So we look at this dependent variable part, the d, and we see the 468.01 here. And that happens when we have a v of 80 miles per hour. So this is a type of problem we've seen before. Now what we're going to do is we're going to formalize this. We're going to give it the name of an inverse function, and we're going to change the notation a little bit. So this is kind of long and clunky, and I've often gotten questions about what am I supposed to be doing when I have a question that looks like this. So our new notation is going to look like this. So we have d, which is the name of our function. We're going to put in the exponent a little -1 there, which means d inverse. So we're looking at the inverse function. And we would be looking to go backwards from the value of 468.01 feet. Okay? So this d inverse is going to take our distance and it's going to return a velocity. So we'd say d inverse of 468.01 is equal to 80. Okay, so that's what our new notation is going to look like. And let's define what an inverse function is. So suppose f is an invertible function. And there are functions that are not invertible, or you have to restrict their domain. And that is a topic further on in the book. But for right now, we're going to just kind of look at the basics of how inverse functions work. So we're going to let y equal f of x and let x equal g of y. And we're going to call these two to be inverses of each other. So for y equal to f of x, the input variable is x. And what we get out of that is y. So here I have x going to y, and we're using f of x as our function. For g of y equal to x, our input variable is going to be this y, and the output variable is x. So f of x goes this direction, g of y is going to go this direction. So there's our g of y. Okay, so they kind of go round and round, back and forth. Okay, there's some special properties that come with this that we're going to look at in a little bit. So to write g of x as an inverse, we're going to change this notation, and the notation will be f with a little -1 up there. And this is read as f inverse, or whatever letter your function is. And then one thing to note really quickly, so this is a common misunderstanding with this -1 kind of being in that exponent slot. If we have the whole quantity, so this is all of f of x raised to -1, that is equal to 1 over f of x. Okay? But if that -1 comes between the f and our independent variable, then we're talking about the inverse function. Okay, so two different ideas here. This one with the -1 on the outside is 1 over f of x. The -1 comes in between your function and your independent variable, then we're talking about the inverse function.